Hi guys, in this lecture we will be starting with the load flow analysis. So first of all, what the question that comes to mind is what is meant by load flow analysis. So basically load flow analysis is a process by which we wish to determine the voltages at each and every bus of the power system. So we wish to calculate the voltage magnitude at each bus, the voltage phase angle at each bus, as well as the real and the reactive power flow in the transmission lines. So it is basically a steady state solution of the power system. Now the problem is whenever we wish to calculate the parameters of a power system, then the power system must remain as it is. That is, there must be no change in the power system, or it must be static. Now, but as we know, there are multiple loads connected in a power system and loads depend on the consumer. So the load on the power system will be continuously changing. So it becomes a big problem how to tackle the continuously changing loads in the load flow analysis. So what we do is we take a snapshot of the power system. What is meant by snapshot? We save the state of the power system, that is the state of the loads. We save the values of the loads at some instant and then we analyze the power system to determine the voltage magnitude and the phase angle. If you take a snapshot or if you save the values of load at a single place, then those loads will be non-changing. It is also called as offline study. So basically, load flow analysis is an offline study of a power system. What is meant by offline is the values that I am using is not the current operating values of the system, or that means the system that I am analyzing is not operating. An online study means we will be conducting the study of the system when the system is in working condition. Okay, that means whenever the power system will be delivering the load, at the same time if you are doing the study, it is known as online study. But whereas if you take a snapshot of the power system and save it in the system, it will be called as offline study. So load flow analysis is nothing but analysis of the power system offline. Now what is the motivation behind the load flow analysis? Now we will add some apparatus or remove some apparatus like load, transmission line or transformer. We will be adding or removing such sort of apparatus continuously from a power system and we wish to calculate the effect of these things on bus voltages. That can be done by means of the load flow analysis. Now, since we are also determining the voltage angles, so we can determine delta naught, that is initial operating angle. Now we know the stability margin for steady state stability is 90 minus delta naught. The farther away from the 90-degree we are, the more stable is the system. So we can calculate the steady state stability based on the load flow analysis. For transient stability delta CR, we have cos inverse PM delta max minus delta naught minus P max 2 cos delta naught plus P max 3 cos delta max divided by P max 3 minus P max 2. That means critical clearing angle depends on initial operating angle delta naught. Delta naught is always determined on the basis of load flow analysis. So it also helps us in deriving the transient stability of the system. Now by means of load flow analysis, what I can calculate is mod V. Now suppose it does not belong to 0.95 to 1.05 V rated. Okay, that means it is violating the voltage regulation limit. So we have to use the compensation at that bus. So load flow analysis also helps us decide the rating of compensating equipment, because approximately we saw This was the Q we derived in the compensation, Vs into delta mod V by X. So if you know the voltage is 100 kV and it should have been 90 kV, then you know the boost that you or the decrement that you require is 10 kV. So delta V can be obtained from the load flow analysis, Vs and delta V, which will help us in determining the rating of the compensating equipment. Okay. So that is also one of the advantage of the load flow analysis. Now what are the assumptions that we consider while doing the load flow analysis? Earlier in the stability and the fault analysis, we were modeling generator as excitation in series with a reactance. Here generator will be modeled as complex power PG and QG. Okay, that means generator will inject a power which is equal to apparent power, which is equal to P plus J Q. Now load will be modeled as constant PQ, that is P is constant as well as Q is constant, which is represented by PD and QD. Transmission line is usually replaced by pi model or Z, that is the short line. Is it fine? Now we will neglect harmonics. Why we are neglecting harmonics? Because we wish to operate at a single frequency. Then only the analysis will be easier. Next, frequency is assumed to be constant. Like when we studied stability, we saw that the generator speed changes, due to which the frequency will be affected. But at any instant, whenever you are taking a snapshot of the power system, the frequency at that instant will be constant. Next is no HVDC link. Why no HVDC link? Because then the concept of phase angle of the bus voltage is not applicable. Hence, we have to neglect any DC link. Then we use lumped network. We won't consider any parameter as the distributed. We will lump the impedances into a single element. Okay. So these are the assumptions that we consider while doing the load flow analysis. Now let us basically understand the power flow equations at each bus, which is also called as the load flow solution. So in this figure, we have shown one of the buses of the power system, which is the bus I. So here we have a generator connected to bus I, which is supplying a power of PGI plus QGI. We also have a load SDI, which is PDI plus QDI. So the net power at the bus is PI plus JQI. That is the complex power injection at bus I. So what will be PI? PGI minus PDI. What is QI? QGI minus QDI. Now, when we wish to calculate the complex power SI, which is PI plus JQI, it will be equal to VI into II conjugate. Now, in terms of Y bus, II can be written as YI1 V1, YI2 V2, YIN Vn. Now if you wish to take the conjugate, you have to take the conjugate of n terms, each of which is a product of two terms. So that will be a bit more complicated. So let me take the conjugate of this equation on both sides. So SI conjugate is VI conjugate into II. Now here we will represent the voltages as Vk is mod Vk angle delta k, and the elements of the bus admittance matrix Yik will be mod Yik angle theta ik. So now if we wish to calculate SI conjugate, it will be mod Vi minus delta I into II, which is sigma is equal to J is equal to 1 to N mod Yik mod mod Yij Vj angle delta J plus theta ij. Now, if you take Vi inside, sigma j is equal to 1 to n mod Vi mod Vj mod Yij angle delta j minus delta I plus theta ij. Now if we separate this equation into real and the imaginary parts, Pi will be mod Vi mod Vj mod Yij cos of delta j minus delta I plus theta ij. Similarly, Qi will be minus j is equal to 1 to n mod Vi mod Vj mod Yij sin of delta j minus delta I plus theta ij. So these are the equations for the real and the reactive power at any bus. Okay, so that is called as the basic load flow solution. Okay, so Pi and Qi are also called as the real and the reactive power injected at bus J or at bus I. Now if you see at any bus we have 4 variables. What are the 4 variables? Mod Vi, delta I, Pi, Qi. So for n buses, how many variables will be there? 4n. But the number of equations at each bus are only 2. One for Pi and other for Qi. So total number of equation will be 2n. Whenever the number of equations are less than the number of variables, it results in infinite solution. So what we have to do is, we have to consider or we have to assume rest of the 2n variables, or we can say 2 variables at each bus. You have to assume 2 values of 2 variables at each bus, then the other 2 variables can be computed. So based on whatever values you are assuming or what are the variables you are considering to be known before the analysis, we classify the bus into different categories. So first category is slack bus, which is also called as swing bus or even reference bus. Now whenever you are doing nodal analysis, you need to consider a reference bus. Now usually what you do in nodal analysis, we take the reference potential to be 0. But here we take the reference potential to be 1 angle 0 if it is not given already. If in any question the potential of the slack bus is not given, you can assume it to be 1 angle 0. It is the reference bus in the power system. So what values will be known? Mod V and angle delta. What will be unknown? P and Q. Now the purpose of this bus is to provide a reference for the nodal analysis as well as provide the net real and reactive power required by the power system. Okay. Now what is the net real power? It will be demand plus losses minus generated power. Generated power should be except slack bus. Okay. So if it has to supply the net power, then it must have that much reserve power. If it has to have a higher reserve power, then it must have a high capacity. That is why in our power system we will choose the slack bus as the bus having the highest capacity generator. Okay, but practically there is no existence of the slack bus. It is just for the purpose of nodal analysis. One of the nodes is assumed as a reference. Okay, so that is the concept of the slack bus. For any load flow analysis, one bus needs to be considered as slack bus always. The next type of bus is called as generator bus or PV bus. Now as the name suggests, PV bus means real power and magnitude of voltage is known, whereas reactive power and delta is unknown. Now usually generator has a capacity which it will deliver to the power system, that is real power, and terminal voltage is kept constant by the action of AVR, that is automatic voltage regulator. But at the same time we specify some limits for the generator reactive power. That is, the reactive power must always lie between minimum and the maximum values. Okay. So, if it violates such limits, that is, suppose if somehow generator reactive power goes below the minimum and above the maximum, that is, suppose QGI is less than QGI bin, then what I will do is I will consider QGI as constant, which is equal to QGI min. Similarly, if QGI is greater than QGI max, then it will be considered as QGI is equal to QGI max, which is also constant. Since P was already known, now Q is also known, it will be considered as a PQ bus. So whenever the generator reactive power violates the limit already specified, then a PV bus is converted to a PQ bus. Remember this concept. Okay. So at every step we have to check whether or not the reactive power of the generator lies within the limit specified for that particular generator. The next type of bus is called as load bus or PQ bus. Now earlier also I told you in assumption load is modeled as constant PQ, that is PD and QD. So load bus is where P and Q are known. What is unknown? Mod V and angle delta are unknown. So that is your load bus. Okay. And the last category is voltage controlled buses. Voltage controlled buses are those where we apply compensation to control the voltage. Now the basic purpose of compensator is to supply the reactive power. That means real power will be taken as 0. So these are also considered as PV buses because P is 0 and voltage is known. How come the voltage is known? Because whenever we are using a compensator, then we clamp the bus voltage to a fixed value. Now here if you take the shunt capacitor, that is also used for compensation, but it will be considered as a PQ bus. Remember this concept. Shunt capacitor and shunt inductor will be taken as PQ bus. Other compensation techniques like SVC will be considered as a PV bus. So this is a very important concept. Actually, fixed shunt capacitor or shunt inductor behaves as a constant impedance load, but we model the load as constant P and Q. So it is very conflicting whether to consider it as PV bus or PQ bus. So our first choice is we consider it as a PQ bus. Now let us see some iterative methods to solve for the voltage magnitude and the phase angle. Why iterative method? Because we will be going on calculating in a loop, and whenever we gain sufficient accuracy, that will be the solution of the power system. It is actually a numerical solution of the power system voltage and the angles. The first method that we consider is the Gauss method. Now just now we derived SI or the complex power injection at bus I was VI conjugate sigma j is equal to 1 to n Yij Vj. Both of these are phasors. Now we need to calculate Vi. So Vi at n plus 1th iteration we need to calculate. So what you do is divide Si by, sorry, this was Si conjugate by Vi conjugate, that is Pi minus jQi by Vi conjugate. It will result in sigma Yij Vj. Now suppose I extract the ith term, so I will write j is not equal to I plus Yii Vi. So I have separated this term. So from here I can write Vii will be 1 by Yii Pi minus jqi by Vi conjugate minus summation j is equal to 1 to n, j is not equal to I, Yij Vj. Now what happens is, if you see here, the voltage Vi depends on its own value. So how to differentiate? We will take the k plus 1th iteration. Here it will be kth iteration. Okay. That means the k plus 1th iteration of the voltage will be derived based on the kth iteration of the voltage at each bus. Okay. So that is the method to derive the bus voltage using the Gauss method. Now let us see what is the step-by-step procedure to determine the bus voltage. So first case we are considering whenever there is no PV bus. Now suppose there are n buses. One bus will be considered as slack. If there are no PV bus, then PQ buses will be n minus 1, because there are three categories: PV, PQ and slack. Now first step is to construct Y bus. For load flow analysis, always the first step will be to construct the bus admittance matrix and assume Vi as 1 angle 0 for all PQ buses. That is for 2, 3 up to n. Okay, because I is equal to 1 corresponds to slack bus, and at slack bus the voltage and the angle are already known. For rest of the PQ buses we will assume the voltage. Then in the next step is we will find the complex power injection at each bus. PGI minus PDI, QGI minus QDI. Because these complex powers will help us in determining the bus voltage using the equation for the Gauss method. Now we will set the iteration count k is equal to 0. Now if some of you might have studied about the C++, there whenever we use a loop we set initially I is equal to 0. Similarly here the first iteration will be corresponding to k is equal to 0. And we set a tolerance that is 0.0001. Basically the tolerance indicates the accuracy of the computation. If you wish to have more accuracy, then have a lower value of tolerance. But the thing is, the lower the value of tolerance, more is the number of iteration required. That means we always have to trade off between the accuracy and the time of computation. If you set a lower value of epsilon, then you will need to redo the method again and again to achieve at that value. Now, in the next step what we do is, we calculate the bus voltage at each and every bus. We will calculate the bus voltage. 1 by Yii, Pi minus jqi, Vi conjugate at kth iteration, j is equal to 1 to n, j is not equal to I, Yij, Vj for the kth iteration. We will calculate for all I 2, 3 up to n, because slack bus voltage will remain constant. Now, what we do in the next step is, we will check what is the difference between the previous iteration and this one iteration. That is, we will calculate mod Vi k plus 1 minus mod Vi k. If this is less than the tolerance, if maximum value of this, that is, at each and every bus calculate the difference in the previous iterated value and the new value. If that is, the maximum of those values is less than epsilon, which means all the differences are less than epsilon. That is, we have reached to a point where our tolerance is satisfied. Then load flow converges. If it is greater than epsilon, then we will repeat step number 3. If it is less than epsilon, then load flow converges and iteration count is k plus 1. We have to do this much number of iterations. Okay. So that is how you do whenever there are no PV buses specified. So remember, every time we have to check for convergence. How we check for convergence is by calculating the difference between the previous iteration and the new iteration. If it lies within the tolerance limit, then it converges, else it does not converge. Now what happens if we have a PV buses? Now again here we will assume that there are total n buses. One bus will be the slack bus, and let me say that 2, 3 up to m are PV bus. That means m plus 1, m plus 2 up to n are PQ buses. Okay, so that is how my buses are defined. So total PQ buses are n minus m, total PV buses are m minus 1. Now what happens in step 1? In step 1 again we will construct the Y bus matrix, but here since for PV bus the voltage magnitude will be known, so we will consider mod Vi is equal to 1 for all I m plus 2 up to, and that is only for PQ buses, because for PV buses mod V is known. But delta I will be taken as 0 for all I 2 to n, because delta I is unknown for PV as well as PQ bus, so delta I will be assumed for PV as well as PQ bus. Now in step 2, again we will calculate Pi is equal to Pgi minus Pdi, Qi is equal to Qgi minus Qdi. Now P is known for PV as well as PQ bus, so this can be computed for 2 up to n. But Q is not known for the generator bus, so this can only be computed for PQ buses. Now how to find the Qi for PV buses? Qi will be taken as minus summation j is equal to 1 to n mod Vi mod Vj mod Yij sine of delta j plus theta ij minus delta I. Okay, that is the equation that we derived for the reactive power. From here we will calculate the Q for all I 2, 3 up to m. So now at each and every bus I have the real and the reactive power injection. Now again we will set the tolerance as, let us say 0.0001 and iteration count as 0. Now in next step what we did is, we wish to calculate the voltage at each and every bus. In step number 3, we will calculate Vi based on the equation of Gauss's method. Now this will result in mod Vi and angle delta I. But mod Vi will remain fixed for the PV buses, it can change for PQ. So in the next step we update mod V for only PQ buses, but we update delta for PV as well as PQ bus. Now in the next step what we do is, for generator bus we have to check whether or not reactive power lies within the limits. So in the next step again we will calculate Qi for the case of generator bus. So Qi from the equation that I wrote earlier, that is minus j is equal to 1 to n mod Vi mod Vj mod Yij sine theta ij plus delta j minus delta I. Now it must lie within the Q min and the Q max. If it does not, then if it violates the limit, then we will convert the PV bus to PQ bus. So for the next iteration, the count of the PV and the PQ buses will change. Okay. So at every step, we have to recalculate which ones are the PV buses and which ones are the PQ buses. In the next step, again we will calculate the mismatch. If it is less than epsilon, we get convergence, and that to the maximum value of this. If it is greater than epsilon, we repeat step number 3. Okay. If it is less than epsilon, then it converges and iteration count is k plus 1. So that is how we do the load flow analysis for the case of PV buses. Now let me show you an example where there are no PV buses, how to do the load flow analysis. Now here we have been given a 3-bus power system, out of which 2 are the generator buses, 1 is your load bus. And we have been given the transmission line data, which consists of series impedance. So let me calculate admittance. Minus J5, minus J2.5, minus J4. Just I have taken reciprocal of impedance. Now in every load flow analysis, the first step is to find the Y bus. So let me form Y bus. For the bus 1, there are 2 lines from 1 to 2 and 1 to 3. We will add both the admittances. Minus J7.5. 1 2 will be negative of the admittance, J5. This will be minus J9 actually. 1 to 2 and 1 to 3. J4. Then at bus 2, these two, minus J6.5. 1 and 2 will be 5. In bus 2, it will be actually these two. That is minus J7.5. 2 and 3 will be 2.5. Now 3 1 will be 1 3, 3 2 will be 2 3, 3 3 will be 1 1 3 and 2 3 both, 1 3 and 2 3, that is minus J6.5. So this is my Y bus. And we will assign the voltages to the PQ buses. Now here in the next way, we have been given the bus data, that is voltage magnitude delta PG, QG, PD and QD. So if you look at bus number 1, here we know V and delta. So this is my slack bus. On the other buses we know the P and Q, so these are PQ buses. So we will assume V2 as 1 angle 0, V3 also as 1 angle 0. And now we will calculate the power injected at each and every bus. That is S2 will be P2 plus JQ2, that is Pg2 minus Pd2, that is 0.2, plus J Qg2 minus Qd2, 0.1. Similarly S3, that is Pg3 minus Pd3 minus 1.2, Qg3 minus Qd3, that is minus J.6. Now we know the real and the reactive power at each and every bus. The next step would be to calculate the bus voltage. Now we know we have to calculate it for 2 iterations. So let us perform our first iteration. In our first iteration, V2 1 will be 1 by Y22. Y22 was equal to minus J7.5. Then Pi minus JQi, that is 0.2 minus J.1 upon Vi conjugate, that is V2 conjugate, will remain 1 angle 0. Because initially we have assumed 1 angle 0, its conjugate will remain same. Minus, it will be Y21 V1, Y23 V3. Because we take all the combination except V2. That is minus 1 upon J7.5, 0.2 minus J.1. Now Y21 is actually how much? J5, that is 1 2 and 2 1, and then 2 3 is J2.5 into V1 is 1.05 angle 0. 2 3 is J2.5, V3 is 1 angle 0. So this voltage will come out to be 1.047 angle 1.459 degree PU. Now this is the first iteration for V2. Similarly, if we do first iteration for V3. Okay, we will not do for V1 because it is a slack bus. So here will be 1 by Y33, that is minus J6.5. Here we will have P3 minus JQ3, that is minus 1.2 plus J.6. Now this will be minus 1 by J6.5 This will be actually y31 v1, y32 v2. Now y31 is actually J4, 32 is J2.5. J4 into 1.05 angle 0 and J2.5 into 1 angle 0. Because initial value of V2 is 1 angle 0. Doesn't matter what is the new value. So this will be 0.956 angle minus 11.13 degree. So that is your first iteration. In the next iteration, what we do is 1 by minus j 7.5, P and Q will remain same, 0.2 plus j 0.1, but now we will use the updated value of V2, that is 1.047, and if we take conjugate, minus y21, y21 is how much? J5 into V1, V1 remains constant, then y23, J2.5, and the new value of V3, that is 0.956 angle 11.13. So this voltage will come out to be 1.026 angle 2.03 degree pu. Similarly, second iteration of V3 will yield 1 by minus j 6.5. It will be minus 1.2 plus, sorry, this will be 0.2 minus j 0.1 plus j 0.6. Here we will use updated value of V3, that is 0.956, and upon conjugate it will become plus 11.13 minus V3 y31. Y31 is actually minus j4 into V1 is 1.05 angle 0, then minus y32 j2.5. Updated value of V2 is 1.047 angle 1.459. So this will come out to be 0.93 angle minus 9.94 degree pu. So this way we will keep on iterating until we get negligible difference between the two successive iterations. So let me summarize what we have covered in this lecture. We first saw what is meant by load flow, what are the objectives, and what are the assumptions. Then we saw the equations for Pi and Qi, which was Pi minus jqi sigma j is equal to 1 to n mod vi mod vj mod yij angle delta j minus delta I plus theta ij. Then we saw the Gauss's method, in which vi at k plus 1th iteration is given by yii pi minus jqi vik conjugate j is equal to 1 to n, j is not equal to I, yij vj. Okay. And then we saw the algorithm where we have considered PV buses as well as the algorithm where there are no PV buses. In the next lecture, we will look at another method, that is your Newton-Raphson method.